Hello. Today I'm going to be showing you how to use your reference tables to write the names of some organic compounds. So yesterday we started organic chemistry, which is the study of anything containing carbon. And this is a super important field in chemistry. Anyone that is looking to go into the medical profession is going to have to take at least 2 years of chemistry in college, and the whole second year is devoted just to organic chemistry. And yeah, and that is because everything in our body is organic, basically. Like carbon is the backbone of life. It's like the skeleton that everything else is built off of. It's the structure. So, for example, DNA is, a long chain of carbon rings and phosphate groups, millions and millions of those. Every protein and enzyme in your body is made out of strings of amino acids, and at the heart of every amino acid is a chain of carbon atoms. Fats and lipids are long chains of carbon atoms, carbon and hydrogen. Sugars and so many other things are carbon-based molecules, which is why we care so much about them. And one of the first things you learn how to do is write their names. So just as a quick reminder, I know we weren't in school together for the bonding unit. So this was one of the first things we did online. And so it may be iffy, but just as a quick reminder, if you look at carbon and hydrogen on the periodic table, carbon has 4 valence electrons. It has 4 valence electrons, and the magic number of electrons is 8. 8 is a stable number. So carbon is trying to get to a stable octet, and so when it makes bonds, it's going to always make a total of 4 bonds. Every time it bonds to something else, it's sharing an electron. And for example, this carbon has bonded to 4 hydrogen atoms. And because they're all sharing their electrons together, the carbon has 4 of its own plus 1 from each of the hydrogens for a grand total of 8. So we're not going to be drawing the electrons in this unit. It's kind of like implied that they're there. You're going to see drawings that look like this. And every time you see a line connecting atoms together, it's assumed that that means that they're sharing 2 electrons. So here there's 2 electrons, 2 electrons, 2 electrons, 2 electrons, and then the carbon is stable and has 8. So we're going to start our focus on just hydrocarbons, the most basic organic molecules. Hydrocarbons have only hydrogen and carbon, hydrocarbon. And that's it, nothing else. You're going to learn how to name them and maybe a little bit about how to draw them, although I'm not going to ask you to draw them because it's too hard to do on the internet. Maybe I'll figure out a way. And you're going to watch a couple of videos of what they're used for. Okay, so this says drawing hydrocarbons, but it's also how to use reference tables and how to name them. Every name will have at least 2 parts, and sometimes a 3rd part. The 2 parts that it will always have is a prefix and a suffix. And this is where you're going to use your reference tables, table P and table Q. So table P looks like this. These are organic prefixes, meaning the part that goes at the beginning of the name. And it's really simple. You just count how many carbon atoms are in a chain, and that's what goes at the beginning of the name. So if something has 6 carbons, it's going to start with hex. If it has 2, it's going to start with eth. Just so you know how they're pronounced, this is meth, eth, prop, bute, not but, bute, pent, hex, hept, oct, non, or known, I don't know, no name, known, and dec. So when we look at, so the first thing we do is we look at that prefix, and this is a hex. And I know from my table that hex meant 6. So I know that this hydrocarbon, this is going to have 6 carbons in a chain. And it's assumed that they're going to be bonded together. So they're connected all by just one bond right now. Then on table Q, we can figure out what the suffix means. So table Q has a bunch of information, which you'll explore what this general formula means in one of the videos. But the part that we should focus on for now is just the name and the structural formula. If you notice, all 3 of these examples start with F, and we can see why. If you look at table P, F means 2 carbons, and all 3 of these structures have 2 carbons. So what's different is their suffix or their ending. This is ethane, this is ethene, this is ethyne. And when we look at their structures, the difference between them is how many bonds are connecting the carbon atoms together. So if it's just a single bond, then that is ethane. It has an A-N-E ending. But if it has a double bond, that's ene. And if it has a triple bond, that's ine. So we can use that. We go back to our example. This has a YNE ending, which means, based on table Q, that it's going to have a triple bond. So the question is, where would this triple bond go? Does it go at the beginning? Does it go somewhere in the middle? Does it go at the end? And this actually matters because like where that triple bond is affects how it reacts. It affects the properties of the molecule. Like it's a different chemical depending on where this triple bond goes. And that's where this final piece of the name comes into play. If you see a location number, they're telling you where to put the special thing on the chain. So in this case, the YNE told us we're going to have a triple bond, and this 2 is telling us where to put it. Don't put this triple bond in the first location, put it in the second location, like this. Sorry. I hope that makes sense. So one more time just to recap how we use a reference table. This hex part we looked up and it meant 6 carbons in a chain. Then we went to table Q and we saw YNE meant triple bond. And this 2 told us where to put that triple bond. Now, if you're drawing these on your own, you would have to then finish the structure by drawing the hydrogen. So far, we've only drawn the carbon part of the hydrocarbon. And to do this, we would need to keep in mind the fact that carbon always wants to make 4 bonds. It wants to share 4 times so it can be stable. And to figure out how many hydrogens to draw on each carbon, we would look at each carbon individually and see how many lines connect to it already. So like this first carbon has just 1 line connected to it. That's not enough. It needs to have 4. So we would put a hydrogen here. We would put a hydrogen here. Now we're up to 1, 2, 3 bonds. And so it would need to have another hydrogen over here. Now this carbon has made 4 bonds. 1, 2, 3, 4. It's stable. There's like unlimited supply of hydrogens. It's just how much space is there for them on the carbon. Now the interesting thing is this carbon here next to it, because it's already made a triple bond to the carbon next to it, and it has another bond on this side to the other carbon, it's already made 4 bonds. It doesn't have any more room for hydrogens. So there's no hydrogens would go here, or this carbon either. This one also has 1, 2, 3, 4 bonds. We're just counting the lines that connect to the carbons. This carbon here has a single bond to the left and a single bond to the right. That's 2 bonds. So it's going to need to make 2 more. So there would be 1 here and 1 here. Now this carbon has made 4 bonds. And we keep going down the line. This next carbon now has made 1, 2, 3, 4. And then at the end of the chain, this carbon has only made 1 bond. So to get up to 4, it would make 3 bonds. And this would be the final structure of 2-hexene. Maybe I'll find a program that'll let you draw your own. I don't know. What you're going to be practicing today is just writing the names. So you'll be given the structures and you have to write the names. So let's look at maybe one example of that. So your assignment's going to look like this. One thing you'll notice is that, like, if you want to check every single one of these structures, every single carbon has made 4 bonds. And even if they, like, so this one here has 2 carbon atoms, but there's a double bond between them. So there's just 2 H's, 1, 2, 3, 4, 1, 2, 3, 4. So to do this part of the assignment, all you have to do is use reference table P and Q to write the names. So I don't know, let's do this first one together. I see only 1 carbon. And it's all just single bonds. I don't see a double or a triple bond anywhere. So I would go here and I'd be like, okay, 1 carbon, it's gonna start meth. And then single bonds, it's gonna end ane. So let me put it together, methane. Methane, I know that. I've heard of that before. Let's do one more. So like this one over here, I count 1, 2, 3, 4 carbons, and I notice it has a triple bond. So I'd go around my reference tables. 4 carbons is going to start bute, and a triple bond is going to end YNE. So that would be butane. However, be careful. Oh, don't look at that. That was not good. Oh well, you can check your answers against the first half by pausing the video there. I'm not going to re-record this. Teaching. When the chains get longer like this, and you have a choice between like where the triple bond could go, like in the example, you're going to need a location number. So it's not enough for this example to say just butane, bute for 4 carbons, ine for the triple bond, because you could put a triple bond in the first position or the second position. You need to be specific. This is a triple bond in the first position between the first 2 carbons. Some people might wonder, doesn't this count as a position? This is just the carbon-hydrogen bond. Hydrogen can't make a triple bond. Hydrogen's just kind of there to finish the structure. The main parts that matter are the carbon-carbon bonds. So this is a triple bond in the first carbon-carbon bond position. So the full name for this example would be 1-butane. All right, so you've got a total of 12. I've flashed the answers to at least half of them. You shouldn't have too much trouble with this. Yeah, good luck. I'm trying to find the stop recording button. Bye.